Then there are organic compounds. I'm going to go through this kind of fast. Organic versus inorganic was an early division by chemists. Organic compounds were things that came from living organisms. Inorganic came from non-living. The organic compounds were actually easy to decompose, burn, but they were difficult to synthesize. The inorganic compounds were easy to synthesize, but not very easy to decompose. Today we can make anything in the lab. Organic compounds are all around us. They are in us. Chemists use the word organic much differently than people use it, say, at the grocery store. Organic apples versus non-organic apples, the chemist thinks that's ridiculous because all apples are organic. They are living organisms. They have organic compounds. Organic compounds have carbon and hydrogen. They sometimes have some other elements, typically oxygen, nitrogen, phosphorus, sulfur, but the key is carbon. Carbon has covalent bonds, and it always forms 4 covalent bonds. And the cool thing about carbon is it can make these bonds with other carbon atoms or with other elements like hydrogen or oxygen. It can make single, double, or triple bonds, and it often makes long chains of carbon atoms. And so we get some really, really big molecules like DNA that have carbon chains at their base. Here's some examples. These are compounds that only have single bonds, single carbon-hydrogen or carbon-carbon bonds. The carbons can be in a straight line. They can have a branching structure. They can form rings. And then here are some where we have a double bond. This is a triple bond between carbons. Here there's a double bond between carbon and oxygen. These are all examples of organic compounds. So if we add this into our overall nomenclature, we're starting out with all compounds. We have inorganic compounds. That's what we learned about the molecular and the ionic and the acids. Those are inorganic compounds. And then organic compounds. And these can be divided into hydrocarbons, which contain hydrogen and carbon, and things that have more stuff, functionalized. They're called functional groups because they change the function of the compound. Hydrocarbons are very common, and they're often used as a fuel because they have a lot of energy in them. So oil, gasoline, liquid propane, natural gas, those are all hydrocarbons. If the hydrocarbon only contains single bonds, then as a group they're called alkanes. If we have double bonds, they're called alkenes, and triple bonds are called alkynes. So we use a suffix to indicate what kind of bonds are in there. The hydrocarbon's name is a base name. The base name is determined by the number of carbon atoms, and the suffix is determined by what kind of bonds there are.
So double is alkenes and then triple is alkynes?
Yeah. So the base name depends on the number of carbons. And if we look at, starting at 5, pent, hex, hept, oct, non, dec, these are the same as the prefixes we used for hydrates and for molecular compounds. They just don't have the vowel at the end. But the first 4 are different. And that's just historical. You know, once people start calling something by a name, it's hard to get rid of it. So it can be confusing. There's meth, eth, prop, and bute, and how do you remember the order? Mom eats pickled bananas. I don't know if anyone else uses that mnemonic, but that's what I've always used. I didn't know you could pickle bananas, but it sounds like Mom might be expecting another baby. Crazy cravings, right? MEPP be. And if I'm looking at, especially like propane or butane, I'm thinking Mom eats pickled bananas in my head before I tell you how many carbons, because it's the only way I can remember. And then the suffix, single bonds only, at least one double bond, at least one triple bond. And so you can take any of these base names and combine it with one of these. So you could have hexene. That would be 6 carbons, at least one double bond. You could have octine. 8 carbons, at least one triple bond. Propane. Propane, 3 carbons, all single bonds. Now, what I'm teaching you here is not even really scratching the surface. We're just looking at the surface of organic nomenclature. But we do need to have just this little baby understanding of it, because some of these names come up during the course of the class. So this is a table, which may or may not be interesting to you, of common hydrocarbons. So we have their names, their molecular formulas, their structural formulas, space-filling models, and common uses. So these are things that are used in everyday life. You can see like ethene, right? The eth means 2 and the ene means a double bond. So here we've got 2 carbons with a double bond. Ethyne with a triple bond. The functional group changes the functionality of the that specific molecule or atom. And so we can put organic compounds with the same functional group into families. The alcohol family, all of the alcohols contain an OH functional group. This is methanol, and this is isopropanol. It's rubbing alcohol, and this is sometimes called wood alcohol. Neither of these things are safe to drink, but they're both members of the alcohol family. And so this is the functional group, the OH, and then the rest of it is just hydrocarbons, and that's often abbreviated with an R. It could just mean any old hydrocarbon. So here are all the different families. There's alcohols. The family that it's in affects the name. So ethanol, the OL tells me it's an alcohol, and the eth part tells me 2 hydrogens. And this is the general formula, where you've got carbons and hydrogens over here, and this is the functional group. In an ether, you've got an oxygen between 2 hydrocarbon groups, aldehydes, carbon with a double bond, hydrogen on one side, hydrocarbon on the other side. Ketones, you've got hydrocarbons on both sides, carboxylic acids, you've got this C double bond O and an OH here, and esters, and then amines have nitrogen in them. And here are places that we might find some of these things. So I don't want you to memorize all of these. I want you to know the alcohol family and the carboxylic acid family and the amine family, just to be able to identify that this formula is one of those. So we should be able to do something like this. Draw the structural formula for nonane. Well, what does none tell me? 9 carbons. So the structural formula, I have to show how everything's connected. The carbons are going to make a long chain. There's going to be 9 of them. 2, 3, 4, 5, 6, 7, 8, 9. That's the typical math you find in organic chemistry. It's counting carbons. Then there's hydrogens. Carbons always have 4 bonds. The ane here tells me that all the bonds are single bonds. So these carbons must all have 4 bonds, so they must have 4 single bonds. And you probably see why we don't always use structural formulas, because this is tedious. So then what are the other things bonded to the carbons? They're hydrogens. So many hydrogens. No name.
If it was a hydroxide connected to that, at least on one end,
Mm-hmm.
would that be a H and a O separately or OH together?
So if we make this into an alcohol, the oxygen and the hydrogen are actually bonded to each other. We usually just draw it as OH, but it's really like this. So this would be nonanol. But we'll go back to what we had before. That's nonane. Okay, so just the prefix or the base gives us the number, and then the ane. What if it asked us to draw nonene? What if this was nonene? Where do we put the double bond? Well, there's actually a whole set of nomenclature rules that tells you where there's a number and it specifies. In this class, we didn't learn any of that. So if you need to draw nonene, you can choose where you put the double bond. Put it anywhere you like. I'm going to put it on the end.
And it can only be all carbons.
But if I have 2 bonds here, and the carbon can only have 4 bonds. So then I have to get rid of a hydrogen here and a hydrogen there. Whether I get rid of the one on the top or the bottom or the end, it doesn't matter, but this carbon can only have 4 lines coming from it, 4 bonds. And then to which family does this compound belong? So we might look at this and say alcohol, but it's also got this piece. This part is just the hydrocarbon part. So that would be this one, right? It's a carboxylic acid. And I'm only asking you to remember 3: alcohol, carboxylic acid, or amine. Mm-hmm. Yeah, so how did I know how to draw nonane? I'm going to make it back into nonane. So the prefix non tells me 9 carbons. There are actually a lot of different ways those carbons could be arranged, but the simplest is just put them all in a chain. Good enough for Chem 1A. So I'm going to draw 9 carbons with single bonds. The ane suffix tells me it's all single bonds. Carbons always have 4 bonds. And so like this carbon is bonded to its neighboring carbon and this carbon, but it has to have 2 more bonds. So I put a total of 4 bonds around each of these, and I just fill in the empty places with hydrogens. Let's do a smaller example. Let's do pentane. So let's do it in a different color. So how many carbons? 5. So I'm going to make 5 carbons in a chain. The ane tells me it's all single bonds. And so I need to give each of these carbons 4 single bonds. And it, just works out conveniently. There's top and bottom, right and left. I've got 5 carbons. None of those other atoms can be carbons. They're all just going to be hydrogens. If I gave you the formula and asked you for the name, you just count the carbons, 1, 2, 3, 4, 5, pent, and it's all single bonds, pentane. Any other questions?